our group is doing synchronous AC motors. So these motors move at constant speed no matter the load on them, as long as the load is in the design parameters of torque. So the way that these work is you have a squirrel cage, and Lon will go deeper into this later, but you have a squirrel cage that kind of acts as an induction motor with the rotating magnetic field in the stator, and that's attached to the rotor, gets the rotor up to synchronous speed, and then the DC power supply is applied and the motor will run at constant speed. So in the beginning, the 3-stage AC supply will be spinning the squirrel cage, acting as an induction motor. This means that it has slip until it gets to synchronous speed. Then the rotor has a DC power supply applied and will move at that constant speed with no slip.
The part that makes it an AC motor is it has a 3-part AC power supply, which is gonna go in here to what is called a stator. That's this outside part right here with these little rods, I guess. Pretty much what it's gonna do is this motor is driven by EMFs, electromagnetic fields, as well as magnets on the inside of this rotor. So these are the magnets right here, and it will be energized later. But yeah, so as it starts, this is as the AC power supply goes in, it creates a rotating magnetic field. So these will change polarity north and south as it's going in order to pull these magnetic rods right here, which will also be inducted so they have a polarity of their own. But the polarity here in these will be constant throughout. And so as it's starting, if we have these on with this DC power supply, that's how they're going to be excited and keep their polarity. If we have these on at the beginning, it's not going to move the rotor, because as this north, say it's moving here, this north is going to repel it, so it moves a little, but then as soon as it meets this south, it's going to be pulled, so it won't move. Like the polarity as it's going across these two will push it and keep it still. So to get around that, it's pretty sneaky. So at the beginning, you turn off the DC power supply, and you have this thing called a squirrel cage. You can see I drawn it in little dash marks right here. It'll go right outside, and also these little rods right here will go right in between these magnets right here. And so what happens is at the beginning, since all of these magnets are turned off, the metal bars on the squirrel cage can be rotated in this EMF. And as it gets up to speed, then we turn on the DC power supply, and then these gain a polarity, and then as it's spinning, the rotating magnetic field will get it up to speed as well, and then they'll lock in. Like this north will be locked onto this north, and that's why it's called a synchronous motor, because they'll...
Alright, so when you're using your AC synchronous motor, you're going to want to know your synchronous speed, which is the speed that the motor reaches when it sets in and stays constant. So to find that, you have your synchronous speed, NS, and that is equal to 120 times frequency all over the number of poles used on the rotor. This is measured in RPM, rotations per minute. So if you want to change the synchronization speed, all you have to do is change the frequency, and you set that new constant speed that the motor will run at. So why would we use some of these synchronous motors? Well, the trick is that it uses AC power and converts that into work. So you can use anything at constant speed just from your AC outlet that you would find in a household appliance. So a few household appliances that would use this that work perfectly are something like a clock or a blender. But we also see it in a lot of industrial uses to run at, and it's even used in electric trains that we see.